next speaker is David van Balen, and he's going to talk about work he did on basically having a very aggressive fusion algorithm, kind of optimal fusion algorithm using integer linear programming.
Thank you. Yeah, so I wanted to kind of jump right in with an example to show what I was talking about. So in this talk, I'm talking about languages very similar to the one Truls was also discussing. So a functional array language where you have combinators like map, for example, to work on these arrays, which compiles down to, for example, parallel GPU code. In such a language, one of the very important optimizations you need in order to generate efficient code is fusion. So the idea with fusion is taking multiple of these combinators, doing something with them, and in the end generating a single parallel loop or a single kernel that evaluates all of these combinators. In this slide, I'm showing one function which has 3 maps, and there's 2 different ways in which you could fuse this function. So there's these first 2 maps, A's and B's. I'm going to refer to the functions by the name of the array that they produce throughout this talk. So these first 2 maps, A's and B's, both take the same input array X's as their argument. So one of the things you could do is fuse those 2 passes over X's together to write a single loop which consumes this array and then produces both of those outputs. Another thing you could do is combining A's with this final map, where you're kind of fusing away the intermediate array A's completely. So the idea here is that during your loop, you're reading an element from X, multiplying it by 2 to get an A, and then immediately using this A in the function argument of the last map. So in this case, you're accessing the arrays B's at the place, at the index indicated by this element A. Hope everyone's with me so far. So these are kind of the 2 ways I would say you could fuse this function. The reason you can't fuse B's with the final map is because there's this explicit indexing operation. And kind of the assumption I make here throughout this talk is whenever you have this explicit indexing, that means you don't know anything about the structure, so you need this array B's to kind of be manifest to be able to read from it at some random index. So aside from map, these are some of the other combinators that I'm supporting in the language I describe in the paper. These might include some combinators you might not know yet, or not include some other combinators which you did expect. If there's time left at the end, I can elaborate a little bit on exactly why I chose specific versions of these combinators. The most important one of this list that I wanted to talk about a bit is gather, which is also the one mentioned in the title of this paper. So the idea with gather is that we've got, it's got 2 arguments, i's and x's, and this first array contains indices into the second array. So kind of computationally what a gather would do is loop over this first array. Every time it finds one of these indices, it looks it up the corresponding element in the second array at that index, and then generates an array with this new list. So it's kind of reordering x's, or part of x's, maybe. So if you squint a bit, that's kind of exactly what this final map is doing here. So you could also, if you know this pattern, you could rewrite this into gather A's, B's, instead of map with B exclamation mark. Once you do this rewrite, then we'll see in the talk that it is actually possible to fuse all 3 of these combinators together in a single loop. But I'm going to talk a bit about the intricacies of when you can and can't fuse gathers. One other small thing I wanted to mention here is that specifically for this gather, you see that it's got this weird L label. Really all this means is at the start of this whole analysis, we're going to give each gather in our input program a unique label, and we'll need those labels later. Okay, so the key ideas that we're I'm going to talk about are, first we're going to formalize this array fusion, so when can you fuse arrays and what's kind of the output of fusion as a binary operation. Of course, you might want to fuse more than 2 of these combinators, which just means you're going to have to apply this binary combinator multiple times. Second key idea is that in order to figure out when we can fuse these gathers, we're going to have to think about the order in which we're consuming or producing arrays. And then in the end, as the title already implied, I'm going to extend one of the existing interlinear programming solutions, which did not support combinators like gather, to also think about gathers. So, this is not quite formalization slide, but this is kind of the intuition between 3 sort of categories of fusion that I will use, mainly to introduce the terminology. So whenever I say vertical fusion, I mean this pattern where we've got 2 combinators one after another, and in this case we're vertically fusing over the output of this mapg function, which no longer needs to be manifest at all. So this array can be completely fused away. So horizontal fusion is just when 2 arrays take the same input, and diagonal fusion is very similar to the vertical case, except we actually will need to manifest this intermediate result as well, because it's going to be needed for some other computation, or maybe the output of our program. In my fusion thing, I'm going to be considering each cluster of arrays, or each combinator, as purely 2 sets, namely the set of input arrays and the set of output arrays that it has. So of course, for an unfused program, each cluster is just going to be a single combinator, and for a fused program, maybe there will be more. So in this case, we're talking about a program, or a combinator or a cluster, which takes as its input arrays all the arrays in I1 and produces the output arrays in O1. And then this is my kind of fusion judgment. It says, okay, given a combinator or a cluster of combinators that turns I1s into O1s, and one which turns I2s into O2s, then we can fuse those 2 together to create this I2O cluster. So this is kind of the notation I'm going to use. So applying that notation to the first example we saw, here we're specifically looking at the first of these fusion assignments, so a horizontal fusion between A's and B's. This translates into fusing A's, which was a cluster from X's to the array A's, and the cluster from X's to the array B's together to create a single cluster which reads from X's once, and then produces both the arrays A's and B's. So that's kind of, this judgment is representing the oval. Then these are sort of the boring part of the inference rules. So this is all the inference rules where no actual fusion happens. We've got a base case. You can fuse 2 empty clusters to create a new empty cluster. And these 4 intro cases are all if one of your 2 clusters is going to produce or consume an array that the other cluster does not care about at all, then this input or output just gets propagated to the final result. You'll notice that some of these have an additional constraint at the top where something should not be an element of a certain set. You can assume that all of these arrays are not a part of any of the sets, but many of these implications are kind of transitively implied if you only assume these few. So these are the more interesting cases where we actually have the vertical, horizontal, and diagonal rules. So let's just look at the first case. Given that we can fuse the rest of the arguments of these two clusters, then we'll have the first cluster have an extra output, x. The second cluster has an extra input, namely the same x. And then we can fuse these two together where the final result will not mention x at all anymore because it is completely fused away. You'll notice that there's an asymmetry here between the left and the right clusters that we fuse. The intuition behind this asymmetry is kind of if you're fusing imperative loops, you'll have to put the body of one loop above the body of the other loop in the resulting thing. Again, diagonal completely mirrors the vertical case, except we're actually still keeping this intermediate result around. So we've got an extra output. And in the horizontal case, we'll have two clusters that both read from the same input, which means that the final fused result will only read from this input once. So far, this is, I would say, not too difficult yet, but it also does not support the kind of gather programs that we've seen in the beginning. So to look at how we can fuse gather, I'll first have a small example here. So here we've got a single program which has first a map and then a gather. It's possible to fuse this into a single loop, but some weird things happen if we directly do the translation. We see that the body of the map itself does not change at all. We still produce an A by applying F to some X. But the gather kind of pushed its index transformation through the map. So at the bottom here, I'm not sure if you can see my cursor, the actual code generated in the place of this gather does nothing. We just take an A and name it as B. And this index transformation is pushed all the way to the top of the function where we're accessing a different X for our map to work on. So in other words, we're kind of doing this map in a different order, and we're going to write that down in our judgment by kind of annotating each array in both inputs and outputs with some order. In the paper, I chose, I think, 0 for left to right order, 1 for right to left order, and any other number corresponds to this unique label that we gave to each gather. So in this case, our fused cluster is going to consume this input i's at order 0, and it's producing its b's also at order 0, but it's consuming its input x's at the order kind of directed by this gather. Here's a slightly different example. The only thing that changed between this example and the last one is that we're actually returning both of the arrays, so also the intermediate result. And if we do just blindly apply the same translation as we did last time, that means that in our generated code, we'll also need to write the output to the array A's. Sadly, doing this, I mean, of course, you have to choose, okay, which index in the array A's am I going to write to? Given that we've read our X from index I, it might make sense to write our A to index I as well. This kind of works. The problem is that we have no guarantee that this array I's actually contain all of the indexes to array X's. So after evaluating this loop, it's possible that we haven't actually written to all of A's. So for that reason, I'm saying that this is not a valid fusion. And the way we can see it's not a valid fusion is that one of the outputs of this cluster is not in order 0 or 1. So in this case, the output A's is in order L. And we're going to impose a restriction that each kind of top-level cluster, so a cluster which we're not going to fuse with anything else anymore, needs all of its outputs to have either order 0 or 1, because that ensures that we're actually going to evaluate the entire array. So here are kind of the updated inference rules. This time we're actually annotating each array in these rules with its direction. Nothing fundamentally changed here, but there's a little subtlety about the fact that these arrays are annotated with their direction. Namely, for example, for horizontal fusion, you can only fuse two operations horizontally if they're both reading from the same array in the same order. It's still possible to fuse two operations that both read from the same array in a different order, but then they won't get horizontally fused. So the resulting loop is going to read from this input array twice. Which is exactly this example. So in this example, which is the one we've seen all the way at the beginning, we've got our two maps and then a gather. It is possible to fuse this into a single loop, but then this resulting loop is actually going to read from our array access twice. Once at order 0, in order to determine what the corresponding A is, which will be used as the index for a gather. And then this gather will use that index to figure out at which place we're going to read the second X for this B's function. All of this works out, but it means that we're going to have to read from the array access twice. So that was kind of the rules for when programs can or can't be fused. But that doesn't really get us anywhere yet. So in order to actually find an optimal fusion assignment, we formalize this into an interlinear program. So the idea with an interlinear program is you've got integer variables, linear constraints between those variables, and some cost function which defines a metric on them. So these variables are going to model our search space. Constraints restrict the search space to only the valid solutions. And then the cost function is going to define the quality of each of these solutions. And we use any existing IOP solver then to find the optimal fusion assignment. There already exists one of these IOPs. It just does not support combinators like gather. So these are the variables it uses. For each two combinators that have an edge between them in the graphs I showed so far, we're going to have this variable x. Whenever this variable is 0, they're fused, and when it's 1, they're not fused. We're also going to define this pi variable for each combinator, which gives a numeric label to each of the clusters that combinators can end up in at the end. So this pi variable is going to be needed to ensure that we don't have any cyclic dependencies. And finally, we have a variable m, which describes whether or not an array is completely fused away. So these are the constraints imposed on these variables. So from top to bottom. For this first one, we've just got some reasonable bounds for pi. If we have n combinators in our language, then no pi will ever need to be bigger than that. Then this second constraint defines an ordering between all these pi variables. So anytime there's a dependency edge from A to B, whether it's fusible or infusible, that means that we're going to need to compute these two combinators A and B either in the same cluster, or we need to make sure that the cluster for A is earlier than the cluster for B. Then our fusion variables are binary. Our fusion variables for infusible edges are restricted to 1. This one means that whenever an edge is fused, so x is set to 0, this restricts the difference between the two pi variables to the size of 0. So it sets them to the same number. This second to last restriction encodes the fact that an array, whenever an array is not manifest, all of its outgoing edges need to be fused. In other words, whenever we're going to need the result of this array outside of the current cluster, the array has to be manifest. And finally, these m variables are also binary. So given that existing work, this is kind of what we built on top of it. We decided that the only real new variables we needed were these d variables to keep track of the order that each array is produced or consumed. So superscript, we have an I or an O for either the input or output, and subscript are the labels of the combinator. So this first restriction, give me 1 second, says that whenever, so G here is again a constant, which is the number of gathers we have, so it's kind of the maximum label that each gather can have. Whenever an array is manifest, that means that the output order of the combinator that produced this array has to be either 0 or 1. That's encoded by this restriction. So this is the restriction. This prevents the problem we've seen before, where we're going to write to only parts of an array. And the second restriction encodes that this is very similar to the one we've seen here, this one. So where this one said that the pi variables of two combinators need to be the same if they're fused, this restriction says that whenever two combinators are fused, that the output of the first one needs to match the input of the second one. And again, it's bounded by these G times binary variable. Then finally, we've got like the combinator-specific things. So any scan from left to right, we're restricting its input and output to 0. Any scan from right to left, we're restricting it to 1. For most of the other combinators, we're just restricting something like the input that needs to match the output order. And for any gather, we're saying that the input order of the gather is always equal to its label. The output order of the gather can be anything. So all of the things we've seen so far kind of describe the search space, which is the main contribution of this paper. Of course, in order to actually use an ILP, you need a cost function. We didn't write any great ones, in my opinion, partly because we don't have any static array sizes in Accelerate, which is the language we implemented this in. But we wrote some kind of dummy cost functions to be able to run this and to get some benchmarks. So we can minimize the number of clusters, we can minimize the number of edges that are not fused, arrays that are manifest, etc. These are the results. There was also a graph, which I didn't put in the slides, to compare the unfused arrays, the unfused programs with greedily fused programs with the best ILP result. That graph was slightly disappointing because, probably because of these admittedly mediocre cost functions, our actual best ILP result might not be the optimal clustering. Anyway, these are kind of the comparisons between the different cost functions that we run. So one thing we notice is that optimizing for purely the number of clusters, it tended to be the worst, whereas most of these other goals tended to perform much better and mainly similarly. I have not been able to find exactly what in flash attention made one cost function be worse than the rest of them. So for context, these are programs which we also took from a benchmark suite where the size of these programs, once kind of elaborated to the intermediate language that this optimization works on, was in the order of 50 to 150 combinators. We use a couple different IOP solvers for this. Disappointingly, the commercial closed source IOP solver was able to solve all of these in like less than 100th of a second, and all the open source ones timed out depending on which cost function you used. So one thing we're still looking at is, it seemed like specifically the number of reads, so also reads and writes, cost function caused most of these timeouts. So it could be that in the IOP that we're generating for those specific cost functions, there's some pattern which the open source IOP solvers are not able to figure out. Okay, so to kind of sum up what we've done. What time is it? To kind of sum up what we've done, we've formalized this search space for what all the possible fusions are. We've extended one of these existing IOP solutions to support, in my opinion, most of the actual combinators that the languages in this space use. The main limitations we have is the cost functions that I've already mentioned. Also, I guess it's more of a design decision, but in order to generate this whole IOP, we're only looking at the actual combinator itself. And as far as the function arguments to the map, for example, the only thing we checked for there is whether it contained array indexes. But we did not do anything special like analyze more patterns within them. So the idea here is really to take the static guarantees that are imposed by these combinators. So we're kind of relying on the programmer using the right combinators and not writing everything in terms of generates and explicit indexing. Another kind of limitation is that this is only a program analysis. Afterwards, you still need to do a transformation to actually generate this fused code. We do have a somewhat working implementation of this, which is where I got my benchmarks from, but it is not production ready. It was barely enough to get these benchmarks. So that's still a work in progress. So again, we're currently working on code generation for these fused clusters. We're considering trying to figure out a way to either calculate good cost functions or maybe learn them through some data techniques. Finally, there's also a bunch of other optimizations, such as in-place updates or work duplication, which seem to really depend on fusion. So depending on which fusion assignment you choose, there are opportunities for in-place updates which may or may not be available. So ideally, we would also take all of these other optimizations into account when deciding on our fusion assignment. Since I think we still have some time, I'm quickly going to say a few words about the combinators that we did choose. So one of the things some of you might be thinking about this gather function is maybe your language does not support gather, but it does have something like a back permute, or similarly for the scatter, you might have like permute and accelerate. The reason that I ended up writing this paper with gather and scatter instead of those other versions is that it kind of turns out that every program you write in those other versions can be rewritten into these versions without using any fusibility, whereas the other way around, you can't. So if you Some of the programs you can write with this gather interface can only be translated into the vector root interface by introducing explicit indexing. So that's kind of, there's a small proof in the paper where I do the translations. So that's kind of the argument for why these are better combinators. Thank you.
So how do you think this work relates to systems like Halide, where Halide has like a programming language in which you write your calculation, and then a kind of separate language for like scheduling, which is meant to control things like tiling and fusion and stuff like that, where I think a lot of the experience in the Halide world is instead of like, we will just throw like some optimizer at it, what you actually are trying to do is mostly enable like performance engineers to kind of iterate on, like look at benchmarks, understand the behavior of the code, and then kind of tweak the schedule kind of manually. I'm kind of curious, like, have you thought about like various kinds of like hybrids where you kind of expose this kind of space of possible fusions as something that like you can both generate via optimizer, but also humans can directly try and modify?
Yeah, I think both approaches kind of stem from the same basic idea where kind of the motivation behind this work is also that within a certain design space, which is the one that's often used by these array programs, you've got relatively a lot of programs that are somewhat small, but are still intended to need to have a very high performance because maybe they're ran on like huge data. And I think both my work and Halide kind of focus on those programs where you can afford to throw either a lot of human effort or a lot of machine compute effort into finding really the optimal solution, because you're going to run the program so long that it makes sense, and because the program is small enough that this effort is valuable. But yeah, the difference is that in this approach, I'm trying to take more of a automated line. We did add force to the list of combinators to give the programmer a little bit of control over, no, I know that this thing shouldn't be fused, but that's the only thing here. So for the rest, I think my ideal is to have everything be automated. In practice, it might not always be good enough to only do this by the machine. Thanks.
Cheers. Thank you for the talk. So I guess I'm interested in some of the technical details of the fusion, which I'm not sure how, maybe they're not super relevant, but either way. So my first thing I was wondering about was like, did you like think about where like your methods like improves over, I understand, accelerates like heuristics for fusion? Like what sorts of specific scenarios, like where are you able to find better fusion sort of situations?
I mean, the current fusion engine that Accelerate uses is really just based on purely local rewrites. And one of the main downsides of many of these approaches is that, let's see, it can't do horizontal fusion at all, for example. It's only looking at this kind of vertical pattern. So that's, I think, a very concrete example where anytime you have this horizontal fusion, then already my approach will probably be better.
I see, thank you.
Yeah, other than that, I think the thing I noticed, so at the start of this work, it was really motivated by, oh, can't we add horizontal fusion somehow? And then after adding that, working on it for a bit, found out that, okay, now that we've added all these different kinds of fusion, suddenly the problem is NP hard. And then I stumbled on this existing ILP work and decided to expand it to also work on the other combinators we have.
Cool. it's a, yeah, maybe I'll ask another one later.
So one of the challenges with fusion is the tension between duplicating work, which can be very expensive, or sometimes it allows much better fusion. So is that something that you have interacted with in here?
Yes, so this current ILP basically doesn't do any work duplication. But at the end, I quickly mentioned that one of the things we plan to like elaborate this with is also look at work duplication, kind of incorporate it into the ILP to make explicit choices about it. Because indeed, in any kind of like local rewrite-based fusion system, it's often somewhat implicit about when work suddenly will or will not get duplicated. And I kind of wanted to make a more informed decision about it. Does that answer your question? Okay.
Yeah, my question was actually on a similar tangent. So you said yourself the cost model is still very much the focus of attention just now. And I think it's great that you have a formalism to talk about this fusion. And actually, I think this might give you leverage to do something like the halide thing, ultimately, because you could express a complex fusion that you really want. But a simple experiment that you could run, and I was just wondering whether you did actually run this, is you showed us these performance figures, and I assume that this was for a multi-core, or where?
This is parallel CPU code. Parallel CPU code.
Yes, but it would be interesting to repeat the experiment with the GPU and see whether you have a similar answer or not. Did you try any of that?
No, because the backend that this runs on only has a CPU backend so far.
Ah, okay.
So it's just engineering work we haven't done yet.
Because I would imagine you might see very different behavior there, just because the ratio between memory bandwidth and compute capability is very different there.
Yeah, definitely. I think optimal cost functions between CPU and GPU will have a large difference between between different GPUs or between CPUs. It will probably be more a small difference with like weighing whether you have a little bit more memory or something.
Yeah, thanks.
Right, so I had another question. Also, I wanted to add to the discussion that sort of is forming. I think automatic fusion is like extremely important because like in applications like XLA, which you have like in all of Python deep learning, there's no notion of like either indicating something should be fused or like having a scheduling language or anything of useful of that sort. So this is like really cool, I think, to like at least talk about the search space that you have. And I was actually wondering, so you showed this judgment, and the judgment is, I understand it's on two like different operators you might want to fuse, but is it's not immediately obvious to me, but maybe it actually is. Is the judgment like, do you have to like backtrack through it to figure out whether like a pair of operators satisfies it, or like I don't quite yeah, what is the, by which yeah, how do you judge which things should be marked in the ILP as like fusible?
That's a good question. So these. So like this judgment kind of just says it's possible
Yeah.
to fuse these two clusters and make the third one. But these rules themselves are in no way like syntax directed or even unique, I guess. Oh, no.
I don't think
Let me rephrase it. I think given, yeah, in our implementation as well, this is true. Kind of, the fusion here is a binary operation, right? And the way it ended up being, given that you're putting all your operations in like topological order, it doesn't actually matter in which order you keep combining these operations, as long as you just keep appending them to each other with this binary operation, you always end up with a like functionally equivalent cluster. And combining two operations with each other, because they're sets, right? These sets of input and output arrays are unordered. You can apply these rules in any order, but also it doesn't really matter in which order you apply them. You always end up with a what I'd say, functionally equivalent cluster.
Yeah, that makes sense. And so actually, on that note, what do you think are the, I don't know if you discussed this in the paper, but what do you think are the limitations of like considering fusion to be like binary? Do you think like this limits the ways in which the ILP can reason about its cost function or anything like that? Yeah.
No, I mean, I guess this whole judgment being binary is something which is kind of isolated to this inference rules part. As soon as we move to the ILP, we no longer have a binary thing there.
Well, there's the edge, right, which says like...
Yeah, sure. I mean, in your graph, of course, you've got edges, and the edges have...
Okay, yeah, sure, sorry, yeah, right, yeah. Okay. Cool, thank you, yeah.
Okay, if we have no more questions, then let's thank David again. And we are